is an unbiased estimator. We're going to go through a couple of examples of finding unbiased estimators, and then we're going to go deeper into theory and finding uniform minimum variance unbiased estimators, a method for quantifying the minimum variance of unbiased estimators, and then talk about where we want to go from here. So first we want to talk about why unbiased estimators. The real answer here is that they're intuitively pleasing. The idea of bias in a mathematical sense or just in a general sense tends to make people a little worried. Are we really not getting at what we want to get at? So it has a nice intuitive understanding. We want to talk about what does that mean for our estimator to be unbiased? How do we quantify that it does not have bias? And then can we find unbiased estimators explicitly and in a nice, easy way? So why unbiased estimators? We want our estimator to be close to our estimate. That's what we want to estimate, so we want it to be close to that, right?
Oh.
No, we don't.
No, we don't want.
Again, we have this idea of there's a stigma associated with bias. We're worried about what could happen with our estimator if it is biased. And the other thing we have to remember here is that when we're talking about an estimator for a parameter, we're talking in the long run. We're talking on average. We're looking at many different samples, trying to estimate our parameter, and doing that a bunch of different times. So the idea of estimation and the idea of bias of our estimator is in the long run. It's not just for one sample and for one distribution. So bias is the difference between the expected value of our estimator and the value of the parameter that it's estimating. That's a pretty simple idea, just the difference between the two. We say that our statistic is an unbiased estimator of our parameter if the expectation of our statistic is the value of the parameter. So say, for example, that we wanted to estimate the mean of a standard normal. We all know that the mean of the standard normal is 0. So we can take many samples and estimate the mean of the distribution, calling it theta hat. And then with many, many samples, we can plot all these different estimates. And we see here that our estimator is centered at 0, which is the true value of our parameter. So in this case, our estimator is unbiased. The most important part about talking about unbiased estimators is quantifying bias and variance. If you get nothing out of anything I talk about today, it's the idea that in estimation, we need to relate bias and variance and talk about the trade-off we make if we accept bias in our estimators or if we don't accept bias in our estimators. And our criteria for this is the mean squared error, which is the difference between our estimate, theta hat, minus our actual parameter, squared. Why do we square it? Because it makes it theoretically nice to work with. So we're really lucky in that we can decompose our mean squared error into our variance and the bias of our estimator squared. The mean squared error here is a measure of accuracy. It's how accurate is our estimator in the long run. And it shows us how close we expect our estimate to be to our unknown true parameter. Again, since bias is an idea that falls across many different samples that we're taking, we want the variance of our estimator to be small so that our estimator does a good job of estimating our true parameter in the long run when we take many different samples. So the best way to think about this is to think about a dartboard. So suppose that theta, our true parameter, is our bullseye. Our yellow dots are unbiased estimators. We see that we have several there because we've taken many samples and estimated our parameter many times, and they're all nicely centered around our estimator. On the other hand, our green dots are our biased estimators, and you'll note that they're very precise. They're really doing a great job at estimating whatever parameter is right around that area, but it's not estimating the parameter we want to estimate. So for any given problem, there may be many unbiased estimators, one unbiased estimator, or no unbiased estimator. And from here we want to go into examples of seeing one unbiased estimator, many, or none. So we're going to start with an example of many unbiased estimators. It's a very, very general idea and not one that we typically use in the real world, but it gives the general intuition behind seeing that there are many unbiased estimators. So we're going to let x1 through xn be random variables that are distributed independently and identically with a PDF f of x given mu, where mu is our finite mean of the population, and we need it to be finite in order so that we can estimate it. And we're just going to pick arbitrary constants, a1 through an, such that their sum is equal to 1. So in order to talk about whether or not our estimator is biased, we need to take the expectation. So what we do is we take the expectation of a1 times x1 on up through an times xn, our statistic. We can break that down since expectation is a nice linear operator, and in the end we find that the expectation is equal to mu. So therefore, because the expectation of our statistic is equal to the parameter we wanted to estimate, mu, our estimator is unbiased.